First, I would like to announce that Langley lectures have been moved to another room. They're not going to be in this room, but in another room outside. You can find a poster outside. The next presentation will be given by Dr. Venezuela from Riga University, who is the co-author of the paper with Professor Zettelmeier. Professor Zettelmeier has received the Kendall Award in 1968, and at that time his title was Hydrophobic Surfaces. The title of the paper today is Surface Dynamics of Flexographic Plates. And Professor Zettelmeier is going to introduce Mr. Venezuela.
We're deep into the process. That's why I want to say a few words about Diego Valenzuela before I turn the podium over to him. Let me say that this was quite a tale. He went to the University of Chile where he got his PhD and a postdoc with Alan Myers at Pennsylvania. In his first year here, a book issued on heat absorption, which was issued by Elsevier and declared to be their book of the year in science. This young man had nowhere to go. He was up already. Diego has a position of senior scientist at Lehigh. We saw a few years ago, as you all did, that manpower was going to be extremely difficult to come by in this field. And we took a look at what we could do to fix things up. One thing we can do is to introduce more research projects, and that means more non-professors, because we're not about to give away the store in the professorship ranks. But it is true that we can get more of these people, and we can teach them to speak English, which takes some time. But Diego has one force up. He is married to a wonderful wife, a Philadelphia girl. Well, with those remarks, which seem to fit Diego very well, I give you him to discuss surface dynamics at photopolymer plates. Thank you very much.
Thank you for your kind presentation. We would like to share with you today some of the work that we have done in the area of the interaction between liquid and solid as applied to a printing process. This is an ongoing project supported by DuPont, and we are very grateful for them for the economic support. I'm going to focus on just three important topics related with this subject. The first one is related with the source of the contact angle hysteresis. The second one is related with the conflicted subject of the characterization of solid surface by means of a contact angle with liquids. And the third one is about the stability of the polymeric surface when subject to different environments. Contact angle hysteresis refers to the presence of two characteristic values for the contact angle of a drop in the surface of a solid. A maximum value which occurs when the drop of the contact line is advancing very slowly in the surface, and a minimum one that occurs or can be measured when some of the liquid is withdrawn from the jaw and the contact line is receding. We did experiment in 10 commercial flexographic plates of advancing and receding contact angle with water. The lower table named them from A to J, and also gave the value for the advancing and receding contact angle. We see that the hysteresis can be as large as 60 degrees in some cases. There are two models that explain this kind of behavior. One assumes that the surface can be considered to be energetically homogeneous with only one intrinsic contact angle, but the hysteresis is the result of a micro roughness. The second model assumes that for practical purpose, the surface can be considered to be smooth, but the presence of different contact angle is a result of different homogeneous patches with different surface energy. To test which one of these models apply to our system, we studied independently roughness and heterogeneity of our plates, first by measuring the roughness of all of the plates, but here I'm showing two examples of microglass. We see the lower bar is about 10 microns. We see that we have a micro roughness in both cases of the order of 2 or 3 microns. To quantify roughness, we use an instrument that's called tamisor that has a stylus with a tip of about 2 microns. The tip was passed over the surface, and the trace was analyzed, and from there we compute two parameters that we use to quantify roughness. One is R sub A, which is the average deviation of the trace with respect to the mean value, which was obtained by equating the area under the curve for fix and the pressure. The second one, delta Q, is the standard deviation of the slope of the trace in the area that was scanned. Value for those roughness parameters for the 10 plates are presented in the lower table. We found significant difference for the roughness of all those among those 10 plates. A much more difficult problem is the one of quantifying energetic heterogeneity. However, we believe that that's related to the chemical heterogeneity of the surface. For that purpose, we quantify the surface by ESCA experiments, and we find that all these plates have different amount of polar groups or polar molecules, such as oxygen and chloride. Well, the next transparency summarize all this data presented so far. Contact angle with water in the 10 advancing and receding in the 10 photopolymer surface versus roughness parameter and versus polar groups and non-polar groups in the surface. We conclude from this kind of experiment that roughness is not really an important factor determining hysteresis, but the most important factor is the presence of energetic heterogeneity, which is the product of a chemical heterogeneity of the surface. for our specific system, which consists of photopolymer plates. The second topic deals with a much more conflicting area, which is the surface characterization by means of measuring contact angle with dead liquid. The general approach assumes that the interface between air and liquid and solid and air can be divided in two contributions, a dispersive and a polar contribution, and that the interfacial tension between the liquid and the solid can be calculated by applying two approximations. One is the use of the Young equation, which is a balance of force in the contact line, and the other is by assuming valid the geometric mean approximation to quantify the polar and dispersive interaction between the liquid and the plate, or any surface in general. By equating the interfacial tension obtained by using the sort approximation, we finally end up with the equation which is widely used for the characterization of a surface in general, using these two approximations. I'm repeating the equation on top, and the way in which these calculations are done, and the way we did is the following. By contacting a non-polar liquid such as methylene iodine and water on the surface, we are able to resolve the two components of the surface tension to the plate, which are shown in the lower left table. We see that we have significant difference in the polarity of these plates as determined by this method, and also we were able to characterize the ink by measuring contact angle in a surface such as polyethylene of a known surface energy. Also, from the knowledge of the total surface tension obtained, for example, using the Denoy ring method, we were able to characterize and divide the dispersion and polar contribution to the total surface tension of this plate. This was done for 6 ink, 10 or 3 solvent-based and 3 water-based. Well, the real test is, after we have independently characterized plates and inks, can we, using this equation, predict what will be the contact angle if we contact the ink with the plate? Well, we did that in both ways. We obtained those contact angles by using this equation and by measuring directly. The result of that comparison is shown in this transparency that shows the value for the experimental contact angle of the ink on the template and they obtained by using the geometric mean approximation together with the Young equation. This said that this approximation is a not self-consistent method of characterizing surface. However, not shown here, must tell you that all these points represent plates or contact angle in plates that are non-polar, and the one that most departure are the ones that are the most polar. This tells us that probably the geometric mean approximation is not a good approximation to quantify polar interaction between liquid and a solid surface. That give more credibility to different ways of accounting for these interactions, such as, for example, acid-base interaction. It has been generally thought that polymeric interface do not change, they are immobile. However, recent experiments have shown that polymeric material will rearrange themselves in order to minimize the interfacial energy with the environment. To test the extent of those changes in our flexoplate, printing plate, we did the following experiment. We took plate A, B, and C, and we submerged in 3 different liquids, water, a water-based ink, and a solvent-based ink. I would keep them there for about 20 days. Every other day we took them out and we tested by measuring advancing and receding contact angle with water. Of course, we also have a control sample for all these 3 plates which are shown in this transparency. This one shows advancing and receding contact angle for plate A, B, and C as a function of time. We see that in the time period of the experiment, this plate can be considered to be that they do not change. However, plates that were submerged in water became more aerophilic, as indicated by the decrease in the contact angle with water or with these plates, with plate A and B and C. And also, we see that the receding contact angle is a more sensitive measurement of those changes. After 25 days, the plates were taken out of the water and left in air, and we see a recovery of those plates probably to the same original state, indicating only chemical changes which indicate that probably polar groups have been rearranged or have migrated in the surface of this solid. The same result was found for the plate that had been submerged in the water-based ink. Again, we see a recovery of this plate. However, plates that were stored in mostly organic environments such as the solvent-based ink become more hydrophobic, as indicated by their increase in the contact angle with water. Again, we see that those plates, they might with time reach their original state. That's all what we wanted to share with you today with respect to this kind of work. Thank you.
Thank you, Mr. Venezuela. Thank you, Professor Dettelmeyer. This concludes the symposium of former chemical laureates. I thank you very much, both the audience and the authors, and particularly Professor Dettelmeyer. It's a great pleasure to have you. The laboratory lectures are given in another room. You will find the sign outside.
The room is just down the hall. It's section, you'll see the section C sign is just exactly down the hall.
I see, so our name has been changed.
Salon F, I believe it is.
Thank you, Jay.
I'm going to stay for lunch. You're going to stay for lunch?
I don't know what it says, Sandra. I have to find it first. Are you going to the language lectures?
Yeah. Language lectures next time.
Yeah.
When is the lunch?
Yeah. Oh, I mean the divisional lunch? No, I'm not going to do that.
Original lunch is that today? Yes, yeah.
We had dinner last night. You missed it. It was a very nice affair.
We had the nicest dinner we've ever been to.
Really?
Not here.
Where was that? Did you still get one? Oh, here. Oh, you were here? Pardon?
Yeah, that's what I was going to
But you did.